All right, today we are diving into a problem that pretty much every single programmer runs into. Now, on the surface, it looks super simple, but when you start digging for the best solution, well, that's when you uncover this core principle of computer science, the endless tug of war between time and space. So, let's get right into it.
You know that feeling, right? That little glitch in the matrix moment where you just swear you've seen or done something before. It's a weird human thing, but it turns out computers get their own version of déjà vu, and when they do, it's got a very specific name.
Yep, in our world, we just call it a duplicate. But the real skill we're going to unpack today isn't just about finding one. Nope, it's about finding it in the absolute smartest, most efficient way possible. That's the game.
So what is our exact mission here? Let's lay out the problem, what I'm calling the duplicate dilemma.
Okay, the mission, should you choose to accept it, is pretty simple. We get a list of numbers. If any number in that list shows up more than once, our program needs to shout true. But if every single number is unique and shows up only once, it should just calmly report false. That's it. That's the whole problem.
Let's look at a couple of quick examples just to make sure we're all on the same page. In this first list, you can see the number 1 appears twice, right? So the output is true. Easy. In the second list, every number is totally unique, so the output is false. Simple enough, right? But the real question is, how do we teach a computer to figure this out efficiently? And that's where the strategy really comes into play.
Our first approach is, I think, the most intuitive one. It's probably how a lot of us would try to solve this if you just gave us a big stack of papers with numbers on them.
Think about it like this. Imagine you have a long, messy guest list for a huge party, and you're worried you invited some people twice. What's the first thing you'd do? You'd probably sort it alphabetically, right? All of a sudden, any duplicate John Smith entries would be sitting right next to each other, making them super easy to spot.
So the process here is really straightforward. We start with our chaotic list of numbers, and then, boom, we sort it. Just look at that. All the identical numbers are now cozying up as neighbors. From there, it's just a simple walk down the line. We just compare each number to the one right next to it. And the second we find a match, like those two ones right at the beginning, we're done. We found our duplicate, and we can immediately return true.
Now, this method absolutely works. It gets the job done, but it has a cost. That sorting step is the most time-consuming part, and it has what we call a time complexity of O of n log n. Now, all that really means is that as our list gets bigger, the time it takes to sort grows pretty efficiently, but it's not a perfect straight line. So it's good, but it makes you wonder, could we be even faster?
And the answer to that question is a huge, resounding yes. We can be faster by using a totally different and, frankly, very clever data structure. So, welcome to the hash table method.
Let's go back to that party guest list for a second. Forget sorting. Imagine this time you have your master list and just a blank sheet of paper. As you read each name from the master list, you just jot it down on your blank sheet. The second you go to write down a name that you see is already on your sheet, bam! You found a duplicate, instantly, no sorting needed.
In programming, that blank sheet of paper is what we call a hash table, or for this specific case, a hash set is even better. You can think of it like a club bouncer with a perfect photographic memory. It remembers every single unique person or number that it's seen, and it can tell you in a fraction of a second whether it's ever seen that number before. So let's just walk through it real quick. We start with our completely empty scene set. We look at the first number in our list, which is 1. We ask, hey, is 1 in our set? Nope. So we add it. Next up is 2. Is it in the set? No. Add it. Same thing for 3. But then we get to the last number, another 1. We ask our set, hey, have you seen a 1 before? And the set instantly fires back, yes. Game over. We don't even need to look at the rest of the list. Our job is done. We return true.
This method is incredibly fast. It gives us a fantastic time complexity of O of n, which basically means the time it takes grows in a perfect straight line with the size of our list. But, as they say, there's no such thing as a free lunch. To get this amazing speed, we had to use extra computer memory for our hash set. This introduces something called space complexity, which is also O of n. So the memory we need also grows in a line with the list size. We just made a classic trade-off. We've traded memory for time.
So now we have two totally valid solutions, and each one has its own pros and cons. Let's put them side by side and really see the full picture.
And this table just lays it all out nice and clean. The sorting method is a bit slower, but it's incredibly efficient with memory. It basically uses no extra space, which we call O of 1 complexity. On the other hand, the hash table method is blazing fast, but it comes at the cost of using up extra memory. See?
Two different philosophies, leading to two very different outcomes.
Okay, so we've compared these two methods. What is the single most important thing to take away from all of this?
Here it is, the key takeaway. In programming, and honestly in a lot of life, there is very rarely one single best way to do something. The right answer always depends on your constraints. Are you working on a tiny device with very little memory? Well, then the sorting method might be your best bet. Do you need the absolute fastest result possible and you've got memory to spare? Then the hash table is your best friend. Understanding this trade-off, that's what separates a good programmer from a great one.
And that kind of leaves us with one final thought. This battle between time and space, between speed versus memory, it is absolutely everywhere in technology. It's in the way video games render these huge, beautiful worlds. It's in how your phone stores all your photos. So I'll leave you with this question. Where else do you see this fundamental trade-off playing out? It's a fun thing to think about.